Next, I want to talk about interrupt. We will talk about the interrupt process I/O and why do we need this, and what kind of procedures that the processor will follow to deal with interrupts. And we'll provide some examples. And this lecture is particularly relevant to Intel architecture. Other processors may have slightly different interrupt organization. We'll talk about several software interrupt instructions and also the interrupt bit that we use to modify the interrupt structure. Also, trap interrupt flag we'll be talking about. Interrupts are useful when interfacing with I/O devices that are relatively slow compared to the microprocessor itself. For example, keyboard, you don't want the microprocessor to keep checking whether there's a key pressed on the keyboard. So this interrupt processing allows the processor to execute other software, including operating system, while the keyboard operator is thinking about what to do next. When the key is pressed, the keyboard encoder will debounce the switch and put one pulse that interrupts the microprocessor. So using a timing diagram to illustrate this. So this is the what's going to happen in a computer system where we use interrupt to respond to the request from I/O devices. The horizontal axis, you can imagine there's a time axis. So as time progresses, the main program will intermittently be interrupted by different events. The first event here illustrated is a keyboard interrupt. So the CPU will be stop the execution of the main program at this point. And during this shadow phase, the processor will know there is a hardware interrupt. It will stop the software execution of the main program and then switch the execution of a special program we call interrupt service routine, specifically for that particular hardware interrupt signal. Once that event is processed, for example, once the keyboard key press event is processed, then the microprocessor will resume the execution of the main program, and so on, until the next time another hardware interrupt event happens. In this case, there's a printer interrupt coming sometime in the future. So this figure is a timeline showing you that typing on the keyboard and a printer moving data from memory, and how that interfere with or mix together with the execution of the main program. The keyboard interrupt service procedure called byte interrupt and the printer interrupt service procedure each take a little time to execute. You do want the interrupt service routine to be as simple as possible. Just putting the data, just deal with the device to acknowledge the interrupt, and you want to get back to the main program as soon as possible. Otherwise, the efficiency will be very low because you cannot carry out the main task, which is executing your main program. Intel's processor include two hardware pins that request interrupts. One is INTR and the other one is NMI. INTR is the regular interrupt pin, and NMI is the non-maskable interrupt, which we will explain a little bit more later. And there's an output pin from the Intel processor, that is the INTA, which is the interrupt acknowledgement. This pin is used to acknowledge the interrupt request from the device through this interrupt request pin. Intel's processors also can handle software interrupts whenever your program that execute explicitly these instructions, for example, INT, INTO, INT3, bound, these are considered software interrupt instructions. So once your software calls these instructions, the processor will respond similar to responding to a hardware interrupt. It will stop executing the main program and then handle this software interrupt. Essentially, it's going to execute a special routine that will deal with this software interrupt. There are two flag bits in the flags register that are tightly associated with interrupt processing. One is the interrupt flag, IF, and the other one is the trap flag. And there is a special instruction called IRET. This IRET must be the last instruction in the interrupt service routine so that the processor can get back to the main program after handling the interrupt. In an earlier lecture, we talked about 3 different ways to handle interrupt: fixed interrupt, vector interrupt, and the vector table. We have an interrupt vector table in Intel-based architectures, microprocessor systems. And this table is located in a very special location, the first 1024 bytes of the memory, starting from address 0 up to 3FF. And each entry in the table is a 4-byte. So we're talking about 256 4-byte interrupt vectors. These vectors are in fact addresses. And with these 4 bytes, you can essentially have a 32-bit address that gives you 4 GB of memory address space. So you can essentially go into a interrupt service routine at anywhere in your 4 GB of memory space. And the way to find out which vector I need to use is by using the interrupt number or interrupt vector. We said this interrupt vector contains the address of the interrupt service procedure. This table illustrates the interrupt vector table for Intel microprocessors. The left column, the numbers, essentially is the interrupt number, and that corresponding to the vector that's stored in this table. The first 5 interrupt vectors are identical in all the Intel processors. So these are reserved by Intel. Intel also reserved the first 32 interrupt vectors. And a part of that, the last 224 vectors are user available. So you can essentially change the addresses that are stored in this table. All of these 4 bytes, the first 2 bytes are the offset, and the last 2 bytes are the segment address. In the next few slides, we're going to talk about some of the typical interrupt numbers used by Intel processors. Type 0 or the interrupt number 0 is the divider error that's coming from a division overflow or an attempt made to divide by 0. Type 1 is the single step or trap occurs after executing each instruction if the trap flag is set. This is very useful interrupt for debugging. If you use GDB, for example, that's one debugging tool available in Linux. Also on Windows, you have similar tools. And in the early days, if you write assembly language program, you can use debug under DOS to debug assembly language program. And these debuggers rely on this trap flag a lot, because trap flag will provide the debugger the capability to single step on instructions. Type 2 is the non-maskable interrupt. This occurs when logic 1 is placed on the end of my input pin to the microprocessor. You can tell from the name non-maskable, which means that it cannot be disabled. Type 3 is a special one-type instruction. It is used to store a breakpoint in the program for debugging. Type 4 is overflow. In type 13, you don't notice this number 13, type 13, but this happens when your program accesses a memory address that's not allocated. In Linux, if you execute a program, for example, if you reference a null pointer, it'll cause a segmentation fault, and that's in fact going to generate this general protection fault. On Windows, in the early days, you see the blue screen. Windows is going to crash, so that's this type of fault happens. There are different subcategories of faults under this type 13. For example, distributor table limit exceeded, write to a code segment that is protected, and so on. So these are all different possibilities will cause this type 13 fault. Type 14 is the page fault, when the OS tries to load a page or memory that is not currently in the memory, because it referenced the virtual memory pages. After the virtual to physical translation, you may find out that the physical page is not currently in the physical memory, so that will cause a page fault. Type 16 is coprocessor error, which comes from a coprocessor. The next few instructions are so-called the software interrupt instructions. We have int or int3, bound int0. Also, we have IRET, which is a special instruction that's used to return from these interrupt service routines. This bound instruction takes two operands that compares a register with two words of the memory data. Interrupt O checks the overflow flag. Int N instruction is calls the interrupt service procedure at the address represented in vector n. For example, in a DOS environment, if you call DOS or BIOS functions, remember you do int21. That's this software instruction. With this instruction, the processor will go to whatever address that's stored in the interrupt vector table at index 21, or in this case n. So it'll use that as the new address, go to the special program to complete the software request. INT3 is very interesting. This is a 1-byte instruction. When you compile a program with debug mode enabled, for example, if you do gcc-d, that will enable the debug mode. And then when you do debugging, you can set breakpoints, right? You can say, I want to break at line 37 of my main program, main.c. When you do that, the debugger actually inserts INT3, this 1-byte instruction, in the binary code. And so the processor, when you hit C to continue the execution inside the GDB environment, it will proceed executing your main program. But when it hits that breaking point, the breakpoint, it actually hits that INT3. That's how the processor will stop the execution of the program and then give you the GDB prompt to let you inspect the variables, etc. IRET is a special return instruction used to return from software or hardware interrupts. It's similar to the subroutine RET. It retrieves the return address from the stack. So that was a very brief overview of what type of interrupts that Intel processors support. In the next few slides, I want to go over some details regarding the real mode interrupt. While the processor is executing its current instruction, at its own hardware, it will determine whether an interrupt is active by checking the following things. For example, it will check whether there's a single step trap flag is asserted, whether there's a non-maskable interrupt, or if there's a coprocessor error, or there is a hardware interrupt signal asserted, and then it also checks if there's the next instruction is an INT instruction. And it follows this order. If one or more of these conditions occur, the microprocessor will do the following things. It will push the flag register to the stack because it knows that it's going to handle interrupt service routines. In order to be able to get back to the main program properly, then it has to save the flag register onto the stack. It'll check if the interrupt flag and trap flag is asserted or not. If that is, we're going to clear that. Then also we're going to disable interrupt pin. This is to go into the single step mode. Because in a single step mode, the processor is waiting there. It does not have the capability to respond to additional hardware interrupts. So that's why it will disable that. And then it will push CS and IP onto the stack, because that's to record the proper return address. And then it will go to the interrupt vector table to retrieve the new CS and IP. and that's the CSNIP should be used to fetch the next instruction. And of course, in order to do that, the processor has to know what is the interrupt number, right? Because it used that number as an index to the interrupter vector table. In the protecting mode, things are a little bit different, primarily because in the protecting mode, the interrupt vector table is different. Although the interrupt numbers are the same. In protecting mode, the 256 interrupt descriptors are stored in a so-called interrupt descriptor table, or IDT. If you took Microprocessor 1, you probably remember GDT, IDT, those descriptor tables. And IDT is the one we use to store the interrupt descriptors. Interrupt descriptors tells you the exact location of the interrupt service routine. Although we need to do another level of indexing to get the actual address. The interrupt descriptor table can be located in memory location anywhere in the system, and that's determined by this IDTR. Essentially, IDTR tells you exactly where is that interrupt descriptor table. And each IDT entry contains the address of the interrupt service procedure in the form of a segment selector and offset. Now, just a quick review. Segment selector is not the segment-based register. The selector itself is going to be combined together with the GDT to find out the segment, and also from there you're going to combine with the offset. In this IDT entry, or in this descriptor, we can also find whether the descriptor is present or not at this point. Also, there's DPL, the privilege level bits, to indicate what is the privilege level of the interrupt. And this is an illustration of that interrupt descriptor table entry. It's essentially an 8-byte structure that stores this interrupt selector and offset and flag bits. We have these two flag bits in the flags register, and that are used closely by these interrupt service routines: the interrupt flag and then trap flag. After we push the flag register onto the stack, at the beginning of the interrupt responding procedure, we'll clear these two. The meaning of these two flags is that the interrupt flag is the one that we use to enable or disable external interrupts. It's INTR. Remember, INTR is the interrupt pin that will be asserted by the external devices, oftentimes a programmable interrupt controller, and that's the pin used by the device to notify the processor we have an interrupt. This IF flag is inside the processor itself. It's a register that we can access. We can set or reset this pin. If we set this pin, this IF flag as 1, that means we allow this microprocessor to respond to interrupt. If we clear this bit, that is to say, we do not let the processor to respond to this INTR pin. And this is the flags register. This is the IF bit. This is the TF bit. For the trap flag, this trap flag will cause a trap interrupt. This is type 1 interrupt to occur after each instruction executes. So essentially, if you have this TF as a 1, okay, what will happen is the microprocessor will execute one instruction, just one. Then it will stop. It will stop to where? To do what? It will stop to do the interrupt service routine of this type 1 interrupt. When this trap flag is 0, normal program execution occurs. Okay? So the main reason we have this instruction, this flag, is to allow the microprocessor to give us some opportunity to stop after executing one single instruction. And obviously that's what you need in the case that when you debug a program. You want a single step. You want to have a chance to look at all the variables, all the pointers, all the content in memory after you proceed one single instruction in your program. Okay. These flag bits, the interrupt flag is set and cleared by the STI and CLI instruction. And also you can use other instructions to clear or set the trap flag. In the next few slides, I want to talk a little bit about the hardware interrupts. Basically, we're talking about two input pins. One is the non-maskable interrupt, and the other one is the interrupt request. That's the regular interrupt. When NMI input is activated or asserted, let's say if you see a 1, if the microprocessor sees a 1 on the NMI, it knows a non-maskable interrupt happens. The reason it is a non-maskable is that we want the microprocessor to respond. This could be a very serious condition. To give you an example, let's say your computer system works on a UPS power. Okay? So it's a battery-powered system. Normally, if you have AC operating normal, you have the power is operating normally, then the UPS will not kick in. Once you have a power outage, UPS will kick in, so your system can continue to operate for a certain time. But you do want a mechanism to tell the microprocessor system that if you do not save your work somewhere, chances are in the near future you're going to completely lose power. Okay? So that's the case. This NMI will be very useful. Using this NMI, we can notify the microprocessor that this complete power outage is going to occur in the near future. So the microprocessor should do something special, which is to save the content of the work, the status of the work, to a flash storage or to disk, so that it won't cause any drastic effects. For example, you don't want your data, important data, to be lost completely. This NMI is internally decoded. Whenever NMI is asserted, we know it's a type 2 interrupt. So the microprocessor will go to the index interrupt vector table using index 2 to find out where the interrupt service routine is located. But for the regular interrupt, INTR, it's a little bit different. INTR input must be externally decoded to select a vector. What we mean by that is any interrupt vector can be chosen for the INTR pin, but we will use the interrupt type number between 20 and FF. So why do we have these two numbers, 20 and FF? Recall that we have a 256 entry interrupt vector table. Right? We have those 1024 bytes, and each vector takes 4 bytes. That's why we have 256 vectors in the table. In other words, we can have up to 256 different types of interrupts. The first 32 are kind of reserved by Intel. So that's why we have this number 20 in hex. So starting from this 20 hex number all the way up to FF, that's the actual number we can use as user-defined interrupts. INTA, this is a single line pin. So we can assert this signal if we want to generate an interrupt. But the actual interrupt number has to be sent to the microcontroller. And how do we do that? How do we send the vector number to the microcontroller, to the microprocessor? We actually use the data bus. So when an interrupt occurs, when the external device asserts this INTR signal, it's also responsible for sending in that actual vector number through data bus. Okay, this is the connection here. 3 pins, 2 inputs, non-maskable interrupt, and this regular interrupt, and then we have an output pin, interrupt acknowledgement. Non-maskable interrupt NMI is an edge-triggered input. So it's gonna request the interrupt on the positive edge. So if you see, if you generate a 0 to 1 transition rising edge, this NMI will be triggered. And after this positive edge, NMI pin must remain logic 1 until recognized by the microprocessor. Also, before the edge is triggered, NMI pin must be logic 0 for at least 2 clock cycles. Typical usage of NMI is for parity errors. For example, you have parity errors in your memory subsystem or other major faults, for example, power failure. In the next slide, I'm going to show you a power failure detection circuit that will provide logic 1 to the NMI. And in the circuit, we have a optical isolator to provide isolation from the AC power line to the circuit on the motherboard. Let's see. And we assume power supply has at least 75 milliseconds after the AC power ceases. So what we see here, this is a circuit that we can use to report a power failure to a microcontroller, microprocessor, using the non-maskable interrupt. What we have here is, this is the optical isolator we talk about. This is the sensor for the AC power line. So normally, if we have AC power, this transistor will conducting power. So this point here will be a logic 0 in normal situations. That means we're going to have a 1 here, and then we have a 1 here. This is a D flip-flop. We have a 0 on the Q bar. So essentially, in a normal case, we're going to keep 0 at this NMI output pin. When we have a power failure, this point here, because this transistor will stop conducting current, so this will be pulled to high because of this pull-up resistor here. After this inverter, we'll have a 0, so that's a change from 1 to 0. As a result, this Q bar will have a change from 0 to 1. So that's a rising edge. And that's exactly the trigger we would like to have to notify the microprocessor there's a non-maskable interrupt happens. And once that happens, in our case, we would like the microprocessor to go to the interrupt service routine of this NMI, and ideally this microprocessor, because we still have 75 millisecond of power, and hopefully during that time the microprocessor can save most of the work. INTR and INTA, this pair is used to do the interrupt request and interrupt acknowledgement, and both of them, INTR is level sensitive, which means that it must be held at logic 1 to generate the INTR. This INTR will be set by the external event and will be cleared inside by the interrupt service routine. Once the microprocessor accepts the interrupt, it will disable INTR, so there's not another one coming in. And it will enable this INTR pin after it returns from the interrupt service routine. For later processors, there's another interrupt return instruction, IRETD, that's used in protect mode. So let's look at the next slide is a timing diagram where we have INTR, INTA. Also, we have data bus where we see how the interrupt vector is pushed in to the microprocessor to indicate what type of interrupt it is. What we see here is this is a timing diagram for the INTR input and INTA output. As you can see, this data bus D7 through D0 during the second pulse from the INTA, a vector number is put onto the data bus. This vector number is going to be read by the microprocessor. And this is the number going to be used by the microprocessor to determine what is the number of the interrupt. From 20 to FF, what is the exact number? Here we have an example. In this case, we have a set of resistors, and they are connected to this VCC, and also on the other end they connected to this data bus. This is a very simple method for generating interrupt vector FF, because when the interrupt happens, the INTR will be asserted, and when the microprocessor acknowledges that, it will starting to read values from the data bus. Because of these pull-up resistors, these are all logic 1s. So as a result, in this case, if you do a connection like this, the microprocessor will always read FF as the interrupt vector, interrupt number. In the next figure, we're going to see a similar design where we want to generate a interrupt number 80. And we use the INTA, the interrupt acknowledgement, to enable a 244 buffer, 3-state buffer, to supply that interrupt vector. What we have here is this is the data bus, and this INTA is going to be used to enable this 3-state buffer. So whenever this is a 1, okay, this 3-state buffer is going to be set the output as high impedance, which means whatever value here will not affect this data bus. When this INTA is asserted, means this is 0, these tri-state buffer will be outputting the values that's determined by this set of switches and pull-up resistors. These switches provide a way to connect one end of the resistors to ground. If that's the case, for example, if this switch is closed, this is going to be a logic 0. If the switch is open, this is going to be a logic 1. So with this set of switches, you can select a number, and that number will be used as the interrupt number. So in our case, if we want to have interrupt type number 80, what we need to do is essentially we're going to set this as a 1, right? Because we want this as a 1, all the other are zeros. So we're going to close all these switches and leave this first switch open. Again, this is a set of resistors function as pull-up resistor because they are connected to the power. we can use the D flip-flop to convert edge-triggered input to the level signal required by the interrupt pin. In this design, we have a D flip-flop, and we have the edge trigger interrupt request. So whenever interrupt happens, there's an edge. And we use this as the clock input to this D flip-flop. So whenever there's an edge, that is to say we have a clock pulse coming in, so this D flip-flop will change its state, will update its own state. That's essentially gonna load the value of D to Q and also update Q bar. In bottom part, we have a reset, and then we have this INTA. Reset is served as a control to clear this D flip-flop. So at the very beginning, when the system resets, this is going to be a 1. So I have a 0. After this AND gate, we have a 0 to clear the D flip-flop. So we're going to have a 0 output on the Q. When edge trigger happens, because this is a clock pulse, so this value of 1 will be updated to Q, and that's how we generate a interrupt. We can have different ways to expand the number of interrupts. The next figure I'm going to show you is one circuit that can be used to accommodate up to 7 additional interrupt inputs. And the change compared to the early design is the 8 input NAND gate. So the change is mostly here, and this is a NAND gate, and the input to this 8 input NAND gate are all these interrupt requests that may be coming from 8 different devices, and all of them are active low. So in normal case, let's say no interrupt coming from any of these devices. What you expect to see is all these inputs are 1s because they are active low. And after this NAND gate, you're going to have 0 as the input to this INTR pin. So there's no interrupt generated. If any of these devices generate an interrupt, that is to say, if any of these inputs are 0, after this NAND gate, you're going to have a 1. That is to say, any of this device can generate an interrupt. And what's more interesting is that depending on the actual combinations of these devices that generate an interrupt, you're going to present different values here. Okay? Let's say, for example, if I have this first device, this IR0 is a 0, all the other ones are 1s. So in this case, we will generate an interrupt. And because of this tri-state buffer, we're actually sending a value that is 0, 1, 1, 1, 1, 1, 1. So that's the interrupt vector will be received by the microprocessor. So from this actual value, the microprocessor can tell which device or which combinations of devices that generated interrupts. And of course, in the corresponding interrupt service routine, you can deal with these different cases. If you have only one, then that's fine. If you have multiple devices generating interrupts altogether, then you can decide how you do give them priorities.